All right, today we're cracking a scientific case that feels like it's straight out of a detective novel. It's the story of a brand new nanomaterial and the molecular mystery of how it takes down some of the world's most dangerous drug-resistant bacteria.
Okay, so let's set the stage with a problem that honestly affects all of us. For decades, we've had this amazing weapon, antibiotics, but we've overused them, and now we're facing the rise of superbugs, bacteria that have just learned to shrug off our best medicines. Simple infections are becoming deadly again, which means we urgently need to find new ways to fight back. And this is where the race against them gets really interesting. You see, bacteria are brilliant at evolving defenses against chemical drugs, but nanoparticles, they're a whole different ballgame. They don't play by biological rules. Instead, they launch a direct physical assault on the bacterial cell, and that's something these superbugs have no idea how to defend against.
So who's the new hero in this story? Meet MXenes. Now, forget what you think you know about complex drugs. Picture a sheet so thin it's literally just a few atoms thick. The real magic, though, is their surface. It can be tweaked and tuned, making them incredibly promising assassins for these superbugs.
Okay, so let's get into the first big clue, the first piece of this puzzle. It came from a study back in 2021. Scientists were running these powerful computer simulations, and they noticed something really weird happening when an MXene sheet landed on a bacterium. It wasn't just sitting there, it was actively changing the very fabric of the cell.
What they saw was something they called a low-fluidity domain. See, a healthy bacterial membrane is supposed to be fluid, kind of like a choppy sea of molecules called lipids. But wherever the MXene touched down, it created this strange static patch in that sea.
The best way to picture this? Imagine a patch of ice, instantly freezing on the surface of a lake. That is exactly what's happening here. The lipids under the MXene, which are normally zipping around, just stop. They get locked into this rigid, ordered, gel-like state. The MXene is literally freezing a part of the bacteria's skin. And you can imagine the consequences of this are just devastating for the bacteria. That frozen patch gets denser, more ordered, and even thinner than the area around it. This creates a huge amount of physical stress, kind of like a weak spot forming in the wall of a tire. The whole membrane is now dangerously compromised.
But you know, as cool as that was, it wasn't the whole story, not even close. It explained the setup, right, the initial attack. But it didn't explain the final knockout blow. The bacterium was hurt, for sure, but it wasn't dead yet.
So, the big question hanging in the air was this. Okay, stressing the membrane is one thing, but what's the move that actually causes it to completely fall apart? How does the MXene deliver that final killing stroke?
And this is where the breakthrough happened. A follow-up study went back to those simulations, but this time they were looking at the precise forces involved. And what they uncovered wasn't just an attack, it was more like a molecular-level heist.
Okay, so think about it like this. To destroy a membrane, you have to literally pull its building blocks, these phospholipids, right out of it. It's like trying to pull a single brick out of a solid wall. It's really, really hard. It takes about 35 kilocalories per mole of energy. That's a huge energy barrier that keeps the cell safe and sound.
But now, watch what happens when the MXene sheet shows up. That massive energy barrier just plummets all the way down to about 20 kilocalories per mole. That is a huge drop. All of a sudden, an action that was practically impossible is now totally achievable.
And this chart right here, this is basically the aha moment. The MXene isn't just punching the membrane, it's acting like a molecular crowbar. It makes it dramatically easier to just dismantle the cell wall, one piece at a time.
So here's how this heist actually goes down. The MXene's surface is hydrophilic. It loves water. It forms this really strong electrostatic bond with the head of a lipid molecule. This bond basically acts like a handle, making it incredibly easy to just pluck that lipid right out of the membrane, leaving a deadly hole behind.
And what's really cool is that this strategy is totally unique to MXene. Other nanomaterials, like graphene oxide, are more hydrophobic. They tend to grab the fatty tails of the lipids. But MXene goes for the head, and it turns out that's a much more efficient way to pull the whole thing out. It's a completely different and way more effective mode of attack.
So, let's put it all together. When you combine the two clues, the frozen patch and the lipid heist, you finally see the full picture. It's a coordinated, devastating 1-2 punch.
And to be clear, these two things work together. It's a synergistic attack. First, the MXene lands and freezes a patch of the membrane, creating this stressed-out weak spot. Then, from that exact weakened spot, it starts the heist, plucking lipids out one by one until the whole thing just ruptures. Game over for the bacteria.
Okay, so this is all incredibly cool science, but what does it actually mean for the future of medicine? This isn't just some interesting fact for a textbook. Knowing this level of detail could be a total game changer. Because it means scientists can stop just, throwing things at the wall to see what sticks. Now, they have a blueprint. They can start to engineer new nanomaterials with surfaces that are precisely tuned to be even more effective against very specific kinds of bacteria.
I mean, listen to what the researchers themselves said. This is the very first time we've understood how these things work at the molecular level. It's a massive leap in our fundamental knowledge. We now have a whole new playbook in the war against superbugs. And that just leaves us with this one kind of mind-blowing final thought. Now that we understand the mechanics of this molecular takedown, could we one day have an entire arsenal of smart nanomaterials, each one custom designed to hunt down and destroy one specific pathogen on demand? The blueprint is now in our hands.